want to think for a minute now about the pendulum as it descends from its pullback position to its equilibrium position. I've actually exaggerated the distance of the descent here, just so we can draw the vectors and so forth. But if you draw this accurately with a compass and get the arc right, you get an accurate picture. Okay, first of all, as we descend from here to here, your delta y is going to be this. So your change in potential energy is just going to be your delta y dotted with your weight vector, and since the two are along the same line, it's just going to be the product of these two, and since they're both in the same direction, it'll be positive. Okay, the product of the two magnitudes, and it'll be positive. So it'll just be the weight times the delta y. And it's easy to get the expression for the delta y. Just do your trigonometry. You can determine the side of this triangle, and we wrote that out. That's going to be, I'll write it up here. It's going to be L times the cosine of theta, where this angle is theta. And if you subtract that from L, which is a distance from here down to here, don't have room to write that in, but the delta y, I have to write it pretty small, but hopefully you can see this, is going to be L minus L cosine theta, which is L times 1 minus cosine theta. That's written pretty badly, but it's 1 minus cosine theta here. And that's the magnitude of your delta y. Okay. That's that's an important picture. We'll keep coming back to that because we pretty much end the semester on simple harmonic motion, and this is one of your paradigm examples that gives rise to simple harmonic motion. At least if you make the small angle approximation, you get simple harmonic motion. That's a topic that gives people trouble. We're trying to anticipate some of that, and the energy situation here is critical to understanding how simple harmonic motion relates to the motion of the pendulum and so forth. Okay, and taking that a little further, we've got a pendulum here, centers at position B. Now I've got position C, D, and E along the arc of the circle. Okay, so there's a dot indicating position C, a dot indicating position D, and a dot indicating position E. I drew the pendulum a little too big to make those dots equally spaced so that D to E is quite a bit shorter than either of the other two distances. But you still get the idea. Okay, so what we have is we got delta y from B to E. That's from here to here. That's down to equilibrium. It's the same thing we used, we referred to as delta y over here. So delta y from B to E is this. Now we can do a delta y from B to C, and there's a rough spot on the board there. I wasn't able to make that B look very good. Deal with that, but that's BC. And here's your delta y from B to C. And then here's your delta y from C to D. It's this little short vector here because it should be obvious if you're moving along the arc of a circle that the descent from C to D is going to be less than the descent from B to C, assuming these are equally spaced along the arc. And I haven't even attempted to draw the delta y from D to E in here. It's just going to be a little tiny vector. I could draw something here that nobody's going to be able to see it, including me. Okay? The chalk is just too, chalk writes lines too wide to really make that vector. Should be obvious then, and you need to think about this. You maybe should draw your own diagram and convince yourself of this. But the delta y from B to E, that's this, is going to equal your delta y from B to C, which is this, plus your delta y from C to D, which is this, and your delta y from D to E, which is this thing I couldn't draw here. And all these delta y's are going to be negative. And that's going to give rise to negative changes in potential energy. Because remember, your change in potential energy is the opposite of the work done by gravity. If delta y is negative, the weight being down is going to give you positive work done by gravity on the pendulum, but for the reasons that you should understand in terms of what we've done previously, that's going to correspond to negative changes in potential energy. Change of potential energy being equal and opposite to the work done by gravity. So those changes will all be negative, but of course, in this situation, the ideal situation, we have no non-conservative forces. The delta PE plus delta KE is going to equal 0 between any 2 points, meaning that negative delta PEs are going to correspond to positive delta KEs. And you're going to want to think about that, okay? But now we're going to get positive changes in kinetic energy, and the change in kinetic energy from B to E is going to be the sum of the change in kinetic energy from B to C, and the change from C to D, and the change from D to E. You cannot conclude from this that the changes in velocity add up. It's not so. Simply not so. So this is not going to be true. You want to think about it, but this is, you could conclude from the fact that the kinetic energy changes occur for a pendulum bob of constant mass, that the change in V squared, because this is, 1/2 m times V squared here, the change in V squared between here and here is the sum of the changes in V squared for the 3 segments. But that does not guarantee, that doesn't even imply, it's actually contradictory to the idea that the changes in V will add up. The changes in V squared add up to the same thing. The changes in V are not going to add up to the same thing. So you don't ever want to make that mistake from this from the necessity of this equality. Okay, I don't have a set of good words for that, but I think you know what I mean. Okay, so we have all these negative changes in potential energy giving us all these positive changes in kinetic energy that add up in this way. Now, if we go in the opposite direction, because the pendulum could swing back from E to D to C to B, then our delta PE from E to B, and that B is really kind of a bad looking B, but hopefully it's readable, is going to equal the delta PE from E to D and from D to C and from C to B. And those are going to add up, and those are all going to be negative. And we could then make a conclusion if we reverse the direction of the subscripts and all these kinetic energies, we'd still have the same equality, but all the changes in kinetic energy would be negative. Your kinetic energy as you go from here to here, since all your potential energy changes, and I said that absolutely wrong here, are positive. Okay, all your changes in potential energy are positive, so all your changes in kinetic energy will be negative. Well, that just means that as the pendulum swings from here to here, it slows down. Now, it's important to be able to deal with subscripts like this because they can really help with things like relative motion, which is in Chapter 3 that we're about to go back and work through in detail. And there are many cases in physics where you want to be able to think in terms of subscripted variables of this nature. So you want to be sure that you understand how these subscripts work. The general ideas of energy conservation are pretty straightforward here.